In this video, I'm going to talk about basic wave structure. So one of the first things to repeat again is the idea of frequency and period. And we see this concept being applied every time we have an example of harmonic motion, whether it's circular motion or pendulums or springs, and now looking at waves. So frequency in terms of waves is defined as the number of waves that pass a certain point in a given unit time. And the unit for this is the same as it has been before, hertz, which remember is also seconds to the -1 or 1 over seconds. Period for a wave is defined by the time it takes for one wave to fully pass a certain point. And again, period is a time measurement, so the unit is in seconds. And they're inverse to one another, so frequency is 1 over the period, and period is 1 over the frequency. Now, if we just take a really quick look at the ELMO here, so here I have 3 different wave examples, right? So, and you can see that if I were to watch at this point and this wave would go by, it would have an intermediate frequency, whereas this would have a very high frequency because a lot of waves would go by in the same period of time, where this would have a relatively low frequency because less waves would go by in a time. So what's important to recognize here is looking at this, we actually need to define, well, what is a wave? It's a repeating pattern of itself. So what is one cycle of the wave? And in order to do that, we actually have to define some parts of the wave. So let's go ahead and go back to the PowerPoint here. Let's see, my computer's moving kind of slow. So wavelength is written with this Greek letter here. Looks like an upside down Y. It's a lambda. And wavelength is actually defined by the physical distance between 2 crests or 2 troughs, or it's the length of one wave or one wave cycle. And so the unit is actually in meters because it's the length measurement. So let's look and see, well, what is a crest and a trough so we can better define this. So if we look at the wave here, crest is the very top peak of the highest point of the wave, whereas a trough is the lowest point of the wave, right? And a wavelength is the distance of one wave cycle. So if we were to continue drawing here, we would have another crest, and this distance would be the same as here. Or this line shows actually one wave cycle where it goes up and then back down and then back to its original position where it's going to start going up again. So that is actually the wavelength. Now, if we look at it this way, we can actually see multiple waves in together here. So if I were to measure trough to trough, that would be a wavelength, or crest to crest is a wavelength, but it's the same distance as the wave cycle, so going up and down and back to the original position. So those are all the same distances. Now, another idea of we have to define, or another variable we have to define, is actually amplitude. And amplitude, we won't really perform any calculations with this, but amplitude, we have to think about it in terms of energy, which I'll talk about in a later video. So here you can see that this wave is this tall, whereas this wave is a little bit shorter. And this wave height is actually what the amplitude is. And it's the distance between this sort of midline point to the peak of the crest or the bottom of the trough. So that is the amplitude of the wave, and it actually relates to how much energy the wave is carrying. Alright, so we're talking about waves moving past a certain point, so they must have some speed or velocity. We call it propagation speed or wave velocity. And remember, just to keep in mind, remember the particles are not actually moving. It's just the speed of the transfer of the energy through the medium. The particles are moving perpendicular or are sort of just bouncing off one another, and the energy is actually what is moving. Now, the speed of sound in the air is 343 meters per second, roughly, but it can change based on temperature, and we'll talk about that a little bit later when we talk more about sound. But what's important here now is to look at the idea of the wave equation and calculating using these new concepts, right? So we have velocity is equal to wavelength times frequency. That is the wave equation. And I'm just going to jump to the ELMO really quick here so we can look at an example that we have underneath there. So let me open it up. All right, so we can see here that you have these three different waves, right? And we said originally that this one has a high frequency, right? Because there's a lot of waves. Whereas this has a low frequency, right? Now, if we draw in our wavelength, we can see a wavelength here for this, or we could draw it crest to crest, however you want to draw it. Whereas a wavelength over here is really big. So when you have a high frequency, you actually have a very small wavelength. And when you have a low frequency, you have a very large, or we'll just say high or big wavelength. So they are inversely proportional to one another. And so that's why we get this equation of velocity equals wavelength times frequency. Now, we know the unit for velocity is meters per second, right? And I know that wavelength is meters. And remember, frequency is hertz, which is 1/seconds. So if you multiply those, you see how the units match up with one another. So we will be doing calculations calculating wavelength, frequency, and velocity. A lot of times we might be calculating velocity, but again, remember that we just said that the velocity of sound in air is 343 meters per second. And we also know the speed of light in a vacuum, which I'll mention again later when we get to light. But that is 3 times 10 to the 8th meters per second. So sometimes based on what type of wave we're looking at, we actually know the velocity and can use it to calculate the other variables.